Okay, Assalamualaikum warahmatullahi wabarakatuh. Hi everyone. Okay, this is the continue for lecture lateral earth pressure retaining wall. Okay, previously we have covered all the theoretical needed for this discussion, and then we have already learned about a few cases related to lateral earth, and you have calculated some of the cases. So before we move to the other cases, let's do some recap for this discussion. Okay, the case is the basic principle of case is when you have a retaining wall. Okay, you have a retaining wall. Here is your retaining wall, and then behind the retaining wall you have that sword. So to illustrate this one, okay, this is your retaining wall, and the backfill of the retaining wall is your soil, and because of that you will draw this triangle, and that triangle is representing the stress acted behind your retaining wall. Okay, that triangle shows you with different height the stress is different, and the maximum height will be at the bottom of retaining wall, and that maximum stress is given by Ka gamma H. To recap back, Ka is the coefficient for lateral earth, and A is the active condition for lateral earth. And of course, for this one, okay, what you need to calculate is the stress value, and then from stress you calculate for force and find the position for force. If you have triangle, the position for force is at 1/3 of the triangular shape, and then find the moment to find the lateral earth force position. So what you need to do is first find stress. Stress is the maximum value. For this picture will be stress A is equal to Ka gamma H, and force is actually the area of the stress distribution shape. So you have triangular, so that will be half times stress A times H, and then you need to find what is H for that triangular area. That will be H over 3, and moment is actually force times H. Okay, moment, this one is force times H, and then you get your moment value. And to find the position where the PA1 acted, okay, if you have just single diagram, it is simple to look at the diagram, and the diagram is triangle, so the position will be H over 3. Or if you want to have the general equation that we use, it is moment divided by force. So this is how to calculate for the single value for backfill, soil as backfill. You have a single triangle, and that is how you calculate it. So you can find the example from the slide, and you can do by your own. Actually we have already do that, and this is the example that we also have done it. This one is the calculation if you have surcharge. Okay, Q is surcharge, and surcharge is the stress value will be given in the unit of kilonewton per m squared, and that surcharge will be transferred inside the soil. Surcharge, when you transfer inside the soil, it give you the rectangular shape, and that base area, okay, the stress for rectangular shape is Ka gamma Kaq, and then you have another rectangular section or rectangular area because of your backfill, so you have Ka gamma H. So that is the general equation. So still you need to find what is the stress value, okay, what is the force for each of the area, and then what is the H for each of the stress distribution, and then find the moment. So of course to find the position for resultant active force, okay, you have moment divided by force, you get the resultant for active thrust acted to the retaining wall. So that is only a recap. Okay, what you can do is you find example 5. Okay, before that you have example, okay, you have example 1 to 3 for you to do and recap back what is lateral earth pressure for retaining wall discussion. So right now the focus is for example 6. Okay, what I want you to do is to take out your own paper and let's do this side by side. And I want all of you to have your own calculation for this example 6, 7 and 8, and try to calculate more of the example for exercise and also tutorial. So this is example 6. The case is that you have a retaining wall here, and then behind the retaining wall we have different layer of soil. Okay, layer 1, this is what we consider as layer 1, is a different type of soil, and then you have layer 2, you have different type of soil. How we know this is different layer? Because of the properties of the soil is different. Okay, if you can see phi for layer 1 is 30% and 30 degree, gamma 1 is equal to 19 kilonewton per meter cube. But for your second layer, the phi is equal to 50 degree and gamma 2 is 18 kilonewton per meter cube. So this one you need to analyze layer by layer, and let's do this together. So this is what I have already what I already try to do. Okay, what you need to do is to draw the stress distribution layer by layer. Okay, because of the at the back is only soil, so we don't have a surcharge or we don't have water. So what we need to draw first is this rectangular. This rectangular is presenting the first layer for the soil layer, and it is given by Ka1 gamma 1 H1. Okay, because this is H1. Okay, whatever referring to layer 1, you must find Ka1 first to refer to layer 1, and then that one you transfer it down. Okay, when transfer down, that rectangular section will be that triangular section now become rectangular section, which is Ka2 gamma 1 H1. Okay, please remind yourself that when you transfer down any load, let's say from reference 1, and then that one you transfer down. Okay, what you transfer is the load gamma 1 and H1. Okay, but if you have different layer, that one will be Ka2. So that one is referring to layer number 2. What you transfer is only the load, and you need to use different Ka, which is Ka2. So in the layer 2, you also have that triangular section to reflect to soil layer number 2. So that one is Ka2 gamma 2 H2. So in what can conveniently you can do for the calculation, okay, we are referring one by one. For reference number 1, okay, you must calculate for stress 1. Okay, whatever at the base of your triangular area, that one you just take it everything, Ka1 gamma 1 H1. And then for reference number 2, okay, what you have is stress A2, that one is Ka2 gamma 1 H1. And of course you have reference number 3, that one will be stress number 3 is equal to Ka2 gamma 2 H2. Okay, that is how you do it. Let's see how to solve for this one. Okay, I already do it for you. So for layer number 1, refer to triangular section 1. Okay, this is you take the base of the stress value, put all the figure, and then you get the answer for stress A1. And of course you need to find for the force for reference number 1. Force, you must remember, force is always the area of your stress distribution shape. So for PA1, that one is triangular area. So what I do is I take half times, half time base, and then you need to multiply by the height of the triangular. So you have half, the base is stress A1, and then times H1. So you get the value for force for reference number 1. For the height, the effective height for your PA1. So because this is your PA1, we know that PA1 will be acted at the 1/3 of the height. So this is 1/3 of H1. But because of you have another portion here, this one is H2. Okay, that one is PA1 will be acted. Okay, what is the distance for PA1 to the bottom of your soil here? Okay, that one will be H1 times 1/3 plus H2. So that is why I get this value H1 over 3 plus H2. So get that effective value for PA1, the distance for PA1 to acted for your retaining wall. And then calculate for the moment. Moment is, let's say this is column 1, column 2, column 3, column 4, and this one is column 5. Moment is actually column 3 times column 4. So get the value for PA1. So same goes to the reference number 2, but right now for the reference number 2, we have different layers, so you cannot use KA1 as the coefficient. So calculate first what is the value for KA. Given by KA is equal to 1 minus sin phi divided by 1 plus sin phi. Okay, use the find value and then you get the new value for KA. That one will be KA2 is equal to 0.589. So then you refer to reference number 2 here. Okay, what will be the base value? Okay, let's what I have already explained. Okay, you transfer gamma 1 and H1, but because this is already in the second layer, you cannot use KA1, so you use KA2. So this is why at the base for reference number 2 is KA2 gamma 1 H1. So take the value, calculate for the value for stress A2. Okay, then calculate for the force for PA2. Okay, that will be the area. So this one, stress A2 is the base and H2 is the height of the rectangular area. So find the value. And then right now we know because of this is rectangular, the force acted PA2 is the force acting at the center of rectangular section. So that is why the effective height for this one is H2 over 2. So you get 2. So calculate for the moment, column 3 times column 4, you get the value. Now we have another reference, which is reference number 3. This is a triangular area because this one is to represent soil layer 2. So soil always take the triangular shape. So now you must know what is the base value which that will be KA2 gamma 2 H2. So this is the base value for stress A3, and then put all the value, get your answer. And then of course afterward you must calculate for the force. The force is the area of the reference 3 or the triangular reference number 3. Calculate half times the base times the height. So you get the value for 84.816. And then of course you need the effective this one arrow, this one we need to put it there so that you know that for PA3 it is acting at 1/3 of the height of your triangular section. So that is why H2 over 3, and then you get the value. And then of course you need to find what is the value for PA3 moment for stress 3, and then you calculate, you get the answer for moment 3. So next is to total up column number 3 so that you get P total. And then total up for column number 5, you have moment total. And for location resultant, for the location resultant active thrust, so what you need to do is to calculate total moment divided by total force. So you get 2.357 m. Okay, let's say they ask you to redraw this lateral expression. So from the table we can actually see that we have different value of stress and different value of force. Okay, this is the center line. Okay, let's do this with different colors so that you can see. Okay, for us to calculate, okay, let's say this is the value of stress. Okay, this is the value of stress. This one is 0, and then this one is maximum value of stress. Okay, if we want to scale this one, okay, when you see how to redraw, we must look at the stress value. For reference number 1, the stress value is 25 to 308. So I imagine this is the value of 25,308. So I take the triangular area. So that one will be 25,308. So right now, okay, when you see reference number 2, the value is actually 44.764. So that one must be bigger than that, bigger than 25.308. So that is why I redraw that one. So this one is 44.764. And then the value for the triangular reference number 3, okay, I just continue from that one. And then I know that one is 42.408. Yeah, this from this position to this position is 42.408. Okay, if you need to draw P total, so P total at 2.35. So imagine that one is 2.357 meter from the ground. And then we just take all the arrow, that one, that will be the P total. Okay, meaning that P total for this case acted at 2.357 meter, and the value for force that will be acted for this case is 314.488. Okay, that is how we interpret. Okay, you must know how to redraw this one, because sometimes the question is up to redraw the stress ataupun redraw the stress distribution value behind your retaining wall. So okay, please do this. The easiest way, the simplest way, the systematic way is to calculate everything in a table so that you can see everything. Okay, this is whatever you have from the slide, is how to calculate each of the area stress distribution, and then how to find the moment, exactly what we just did, what we have just do right now. And this one is using a longer version of calculating this example in lecture. I'm not using table to calculate. Okay, this is the redrawing of the stress distribution. It is the same thing that I did just now. So you can see that why the diagram is slightly different from the initial diagram that we draw, because of the value of stress is different. Okay, of course you can read about this one, but we need to move on. Okay, we want to calculate for example 7. Okay, example 7 is the combination cases, meaning that just now we are doing 2 layer of soil. You have layer 1 and then layer 2. If you see example 7, it add another one, which is the ground table at the mid boundary. So instead of having 2 layer case, you have 2-layer case plus groundwater at the mid boundary. Okay, of course we need to do the calculation for this one. And of course, before you calculate, okay, the best way to do this is to redraw the diagram first. Okay, let's see that if we can do this before we look at the actual calculation. So what you need to do is to have this retaining wall, and then okay, we have this double layer, and at the mid we have groundwater table. Okay, first thing first, draw the layer 1, a reference number 1 that will be at the first layer. That will be Ka1 gamma 1 H1, and then you are transferring this down. Okay, you are transferring the load K1 gamma 1 H1, but of course because this is the second layer, you are doing for Ka2. And then you have another layer here for soil layer 2. That one will be Ka2 gamma 2, but this one will be gamma dash, and then you have H2. And because of you have that water, we must draw for water distribution, stress distribution. That one is gamma W HW. So this is the height for H1. This one is height for H2. Okay, please recap back. Your Ka is equal to 1 minus sin phi divided by 1 plus sin phi, because we have 2 layers, so you have Ka1 and also Ka2. Okay, this is what you need to calculate first. And because of you have that gamma dash, that one is gamma saturated minus gamma water. Okay, whatever it is, you settle all the calculation first, then we look at the one by one for different stress distribution. So you can draw the reference there, so that you know what is the stress diagram that you are calculating right now. So this is the example that I already did to calculate everything. And of course, for reference number 1 is to look into the diagram number 1, reference number 2 for diagram number 2, reference number 3 diagram number 3, and then reference number 4 is diagram number 4. So I want all of you to redo this example 7, calculate by your own, and then whether you can find the answer, the same answer like what I have right now. So whatever principle that I already explained, it is the same principle. Okay, what you need to do right now is when you have all of this answer, okay, at the end of the calculation, you must calculate for P total, that will be the total force, and then you calculate for moment total, that will be the total moment you calculate. Okay, and then you want to calculate for location resultant active thrust, that will be total moment divided by total force. And of course, what important is you can redraw this one for the stress distribution after you have all the value there. Okay, let's say how to draw it. That one, okay, I have reference number 1. Okay, that will be the triangular, and then I have reference number 2, which is slightly bigger than reference number 1, because reference number 1 it is 25, so reference number 2, that is 44. So my rectangular is slightly bigger than the initial drawing. So when you have reference number 3 and reference number 4, both of them is triangular area. So triangular, you can plus triangular, and then you get bigger triangular. So instead of the value here is 28.720 plus 39.24. It is the combination of these two. So that's why you get bigger diagram for your triangular section. And for you to draw what is the total force acted in this in this case, okay, we have that the position is 2.21, so 2.21 from the bottom of the rectangular section, 2.213 meter. Okay, this will be the P total. Yeah, that is the position for total force acted in this particular cases. In this particular case. So of course the slide is show you one by one how to calculate for KA1, how to calculate for KA2, and then the diagram, and then put all of this in table, and then you can calculate for line of action for the resultant active thrust. So the last and then this is redrawing all of information that you have just now. Okay, of course in this example in the slide, the example they don't show that P3 and P4 is actually can combine. You can draw a big triangle for that one. Example 8 is the combination cases. This is more cases for you to see. Okay, before this you only have 2 layer and groundwater table. Right now you can see that you have surcharge loading, 2 layer, and then you have groundwater table at mid boundary. Okay, of course, first thing first, draw the diagram first for you to have the idea how to solve for this one. Okay, let's try this one to draw. Okay, at this point, of course, our expectation is that if you can see the cases, you can actually know what to draw, at least what to draw. So we have this double layer, you have that Q, and then you have that groundwater table. Okay, and then of course first for me is to transfer the Q first, the surcharge first. That one will be KAQ. Okay, because in the layer 1 you can get KA times 2, and then this one you must transfer down. What you transfer is the load, that is KA, that is with Q, but you have the second layer, that one will be KAQ, KA to Q. Okay, the first layer you have that soil, so that is triangular, and then because of triangular, okay, we need to know what is the base value. Okay, what you will write there will be KA1, gamma 1 H1, and then you transfer that layer down. So you transfer the load K gamma 1 H1, because it is now at the layer 2, so you are using KA2. So in layer 2, another triangular you must draw, because this one is to reflect for soil layer 2, and then you can have that KA2 gamma dash, okay, gamma 2 dash, and then you have H2. And then of course, because of this water, draw another triangular, and then you have gamma W H2. So at least this is the point, you know what you need to draw, and to make you very clear the position of each force or each lateral thrust. Okay, you boleh tulis siap-siap lah kat sini. That one will be PA1. Okay, kat situ position untuk PA2, and then you have that PA3 at the center of that rectangular area, and then you have PA4 also located at the center of that rectangular area, and then you have PA5 1/3 from that triangular area, and then you have PA6. So this is the initial drawing that you must draw before you calculate everything. So for this one, of course, I hope that all of you will redo example 8. Okay, from the drawing, you calculate for each of the area, the reference area, the same thing, you calculate accordingly, and then find the value for the force, okay, the total force here, and then find the value for moment, total moment, and because we want to know the location for resultant active thrust located for this particular case. So redo this one and then find the answer, and of course you will calculate using the slide. This is how they calculate, they show you how the calculation, and then you must redraw. So okay, of course the final thing is for you to know how to draw this one lah. Alright, so this is for today. Okay, we have example 6 up to example 8, and for this lectures, like, you have another example which is example 9, combination cases. So use this one for you to practice your understanding how to calculate for different layer. You have groundwater and then you have surcharge. Okay, that is for today. We will continue to finish this topic under cohesive soil for lateral earth calculation. Okay, thank you.